Hello, I'm Vinicius. I will present my article review on the use of nanofluids in heat exchangers, where a search was made for articles related to the topic. This presentation will follow by nanofluid concept, properties of nanofluids, thermal conductivity, viscosity, and conclusions. The thermal conductivity of nanorefrigerants is low compared to metals, which is the main limitation of development of heat transfer fluids with a great energy efficiency. The nanofluids arose with the purpose of improving this limitation of the thermal fluids so that the nanofluid is a dispersion of nanoparticles, metallic or non-metallic particles with size between 1 to 100 nanometers in the conventional thermal fluids with purpose of improving the thermal performance on the base fluids. Nanofluids are a colloidal suspension of nanoparticles in a base fluid. Nanoparticles can be metals, oxides, carbides and carbonates, or carbon nanotubes. And the base fluid can be water, refrigerant, ethylene glycol, and oil. The thermal conductivity can be influenced by several factors. The main ones are type of nanoparticles, concentration of the nanoparticles, nanoparticle temperature, and nanoparticle size. The type of nanoparticles can be classified into three groups: advanced materials and structures, such as graphene and carbon nanotubes; simple metals with high thermal conductivity, such as gold, copper, silver, and iron; and metallic and non-metallic oxides, such as copper oxide, aluminum oxide, titanium, zinc oxide, silicon carbide. In general, the best conductivity increase follows advanced metals, simple metals, and metallic or non-metallic oxides. Purby et al. Studied graphene oxide nanofluids dispersed in water and compared them with nanofluids containing aluminum oxide and titanium. The results showed that for the 0.1% concentration of nanoparticles, the thermal performance of the graphene-contained nanofluids increased in range of 40% to 300% in relation to pure fluid. For aluminum oxide and titanium, nanoparticles increase of about 27% and 25% was observed. The influence of the concentration of the nanoparticles can be observed in Zhong et al. They investigate titanium in water with concentrations between 0.5% and 1%. Observed that in addition of nanoparticles not only increases the thermal conductivity by 4.2% on average, but also significantly increases the viscosity in 14.9% for 1% of concentration nanofluid. Purby et al. Compared different concentrations of graphene oxide and observed that for high concentrations there is an increase in the pressure drop. In general, the increase in the concentration of nanoparticles increases the thermal conductivity of the nanoparticles. However, there is also an increase in the drop system pressure. Figure 1 shows the performance of different nanofluids at different concentrations, and it is possible to observe the increased conductivity. The figure 2 shows the increase in pressure drop due to the increase in concentration. Abares et al. Found that for water nanofluids with the concentration of 1% uh, iron oxide, the temperature variation of 10 to 40 degrees Celsius represented an increase in thermal conductivity from 2.8% to 18.9%. Henge-Baird et al. Analyzed the thermal conductivity of silicon oxide nanofluid in the temperature range of volume fraction of 25 to 55 degrees Celsius and 0.1 to 3.3% respectively. The results revealed that for the volume fraction of 3%, the great increase in the thermal conductivity of 33% is observed at the temperature of 55 degrees Celsius. The effect of the increase the size of nanoparticles generally tends to decrease the thermal conductivity. Sharpful et al. Investigated the effect of the change in particle size and temperature variation on the thermal conductivity of the aluminum oxide in glycerol nanofluid. The particle size used in the studies was 31 nanometer, 55 nanometer, and 134 nanometer. It was observed that increase in the size nanoparticles decrease the thermal conductivity. Paul et al. Studied the size effect of gold nanoparticles dispersed in water. Their results confirmed decrease in thermal conductivity if the increase in the size of nanoparticle. The first model for thermal conductivity it was Maxwell model. This model consists in high diluted suspension of spherical particles. But this model it was applied for microparticles. Hamilton and Crosser model modify Maxwell model by introducing an empirical form factor. This model is the first model for nanoparticles. The Corsion model was created from the various experimental data through linear regression. Shui created a thermal conductivity model aimed at nanofluids containing carbon nanotubes. In general, studies of nanofluids are associated with the performance of the heat or mass transfer. Therefore, determining the viscous behavior of the nanofluids become essential for the analysis of flow resistance and pumping power. Yapais et al. Revealed that temperature has a large effect on the effective viscous heat in the low shear heat condition, but has little effect in the high shear heat condition. Average et al. Studied the viscosity of the nanofluids containing carbon nanotubes in the very low concentration of 0.005% and 0.03% with water and ethylene glycol as the base fluid. As a result, it was possible to observe that the relative viscosity of carbon nanotubes fluids is not influenced by the type of base fluid. However, at 17 degrees Celsius, the relative viscosity of the nanofluid was greater than 30 degrees Celsius. Jarnet et al., in their studies with titanium nanoparticles dispersed in water as the base fluid, found that the absolute viscosity decreased with the temperature growth, but the effective viscosity remained practically constant, in addition to appearing to be independent of the temperature. The first model for suspension containing spherical particles, it is created for Einstein. Corrosion also created a model for viscosity. The nanofluids are a colloidal suspension of nanoparticles in common fluids that have the potential to improve the thermal properties of the various fluids, thus increasing the efficiency of thermal system. The type of nanoparticles has a great effect on thermal conductivity, so that carbon nanotubes and metal nanoparticles show a greater increase than oxide and non-metal nanoparticles. The type of material has little effect on the viscosity of the nanofluids, with the exception of the carbon nanotubes, which have a lubricating character, and thus decreasing the viscosity the base fluid. Most results show that viscosity and thermal conductivity increase with increased particle load, although the factors described in this review are studied in many modern research. The main flaw in the theoretical research is associated with a lack of predictability and application to determine thermal conductivity and viscosity in different types of nanofluids.